Hi all, so welcome back to the lecture series on solving previous year questions from GATE ECE, and we were solving the questions related to digital electronics. So today we'll solve the questions from GATE 2023. So this is the first question. In the circuit shown below, P and Q are the inputs. So P and Q are inputs, and here Y is the output. The logical function realized by the circuit shown below is, so I need to find Y in terms of P and Q, right? So here when Q is the select line, right? So when Q is equal to 0, the output Y will be equal to I naught, right? That is equal to 0. And when Q is equal to 1, Y will be equal to I1, right? And that is equal to P. So how I can write Y? Y is equal to I naught into Q bar, that is that is when Q is equal to 0, or it will be I1 when Q is equal to 1, right? Fine. So I will substitute I naught is 0 now, 0 Q bar plus I1 is P now and Q. So this is PQ. So Y is equal to PQ. So answer is A. This is the second question. Again, this is from GATE 2023. The question is, the synchronous sequential circuit shown below works at a clock frequency of 1 gigahertz. The throughput in megabits per second and latency in nanosecond respectively are. So we have been given a sequential circuit here, and if you can see here, this is serial in, serial out register, right? So this is the input and this is the output. Okay, so we need to find the throughput. So before that, we will see what is the clock frequency. Clock frequency here is Fc is equal to 1 gigahertz. So what is the clock time? Tc will be equal to 1 by Fc. So this is clock frequency. Okay, and Tc is the clock time. So 1 by Fc is 1 by gigahertz, 1 gigahertz. So this is 10 power minus 9 second, or Tc is 1 nanosecond. Okay, so first we will see throughput. So what is the throughput here? So output here is only one line, right? So we will get only one bit, right? So we will get one bit at a time for every 1 nanosecond, right? So 1 bit per nanosecond will be the throughput. Or I can write like, if I can write like 1 by 10 power minus 9 bits per second I can write, or 10 power 9 bits per second. So here I need in 1 megabits per second, right? So I can write as 10 power 3 into 10 power 6 bits, right? So 10 power 3 megabits per second, that is 1000 megabits, right? So that will be the throughput. Now we'll see what is the latency here. Okay, latency in nanosecond. So what is the latency here? So for that, what we will do, say input is 1 here. So, and this is a D flip flop, right? So for every clock cycle, this whatever is the input D, that will reach at the its output Q. Okay, so if the input is 1 here, it will take 1 nanosecond to reach Q, right? It will take 1 nanosecond to reach here, and the same input 1 will take again 1 nanosecond, next 1 nanosecond to reach Q1, and it will take again 1 nanosecond to reach the output Q2. Okay, so totally it will require 1 plus 1 plus 1, 3 nanoseconds. So latency is 1 plus 1 plus 1 nanosecond, or 3 nanosecond, right? So the answer is A. Throughput is 1000 megabits per second and 3 nanosecond latency, right? Yeah. Now this is the third question. Again from GATE 2023. For the circuit shown below, the propagation delay of each NAND gate is 1 nanosecond. The critical path delay in nanosecond is. Okay, so it has been given each NAND gate is of 1 nanosecond delay. Okay, and we need to find what is the total propagation delay. So if I redraw this here, I have the first NAND gate with input A, and this is Q. This is Q. Okay, and I have the next NAND gate. So this is Q. Fine, and this output is given to this one, and this is P. Okay, so we know here this is 1 nanosecond and this is 1 nanosecond. Okay, so what will be the total time to get here? So here 1 nanosecond and here 1 nanosecond. So this, if we take this path, the total time will be 2 nanosecond. Okay, so that is the so this forms the critical path, right? So whichever is a path, longest path, that forms the critical path. So here if the data comes here as 1, that will require 1 nanosecond to reach here, and the same data to reach here will take 1 nanosecond, so totally 2 nanosecond. So that will be the delay, the total propagation delay of the critical path. Okay, so the answer will be 2. Okay, yeah. Now we'll see the fourth question. The question is, in a given sequential circuit, the initial states are Q1 equal to 1 and Q2 equal to 0. So here in this circuit, Q1 is 1 and Q2 is 0. Okay, for a clock frequency of 1 megahertz. So clock frequency here is 1 megahertz. The frequency of the signal Q2 in kilohertz is, so I need to find what is Q2 and what is the frequency of that. Okay, so since this is 1 and this is 0, this 0 will come here as D1, and since this is 1, Q1 bar will be 0. Okay, so this will be input here. So what happens in the, so initially I will write here Q1 and this is Q2, and initially the values are 1 0. Okay, so what happens in the next rising edge of the clock? This 0 will come here, and here this 0 will come here, right? So next output will be 0 0 at the rising edge of the clock. Okay, so I will draw the next, so this will be the next state. Okay, so here it will be 0 0. Okay, so since this is 0, this 0 will come here, and since Q1 is 0, Q1 bar will be 1, so 1 here. Okay, so in the next clock cycle, or the next rising edge of the clock, this one will reach here at Q2, and this 0 will reach here 0. Okay, so the next output is 0 1. Okay, so again, so now Q1 is 0 and Q2 is 1. Okay, so since this is 0, Q1 bar will be 1. Okay, and here input is 1. So in the next rising edge of the clock, this one will come here and this one will come here. So next is 1 1. Yeah, so now the output is 1 1. Okay, and here it is 1, here it is 0, and now in the next clock cycle or next rising edge, this 0 will come here, this one will come here. Okay, so here it will be 1 0. Fine. So again, so if you see here, this 1 0 has reached, right? So this same 1 0 has again repeated. Now what will be the next sequence? It will be 0 0 0 1 1 1 1 0. So it will repeat. Okay, so that's what will happen. So if you see this sequence just for Q2, you can see first it is 0 0, then it will be 1 1, then again 0 0 1 1, right? So I'll just draw here. The sequence will be for Q2 will be 0 0 1 1. Okay, I'll just, okay, 0 0 110011. Okay, so I will draw the waveform here. It will be like this: 0011 0011. Okay, and I will draw the clock 2. Okay, so this happens in the rising edge of 0 will be at the rising edge of first clock, then next rising edge of the clock, and next clock, like that, right? So in each clock period these signals will come. So if you see here, at each of this rising edge these changes happens. Okay, and if you see here, so the previous value should have been 1, right? So what is the time period of this output Q2? This will be the time period, right? Because it is repeating. Okay, and if you see here, this is the time period of the clock TC. So how many clock required for the entire T? It is 1, 2, 3 and 4. So I required 1, 2, 3, 4 clocks. Okay, so total T of Q2 will be equal to 4 into TC, right? Or if I want to find the frequency of Q2, right? So that is, I will say, right, F2, that is, it will be 1 by 2 Q2, that is 1/4 of, right, 1 by 4 TC, or 1/4 of the clock frequency. So what is the clock frequency here? 1 megahertz, right? 1 megahertz by 4, that is 250 kilohertz. So the answer is 250. Okay, so in other way, if you see here, it took almost 4 clock cycle for Q2 to change, right, or Q2 to repeat. Okay, so it is actually dividing the frequency by 4. Okay, so that's why F2 will be equal to FC by 4. Okay, 250 kilohertz. Yeah. Okay, so that's all for today. Thank you.